over to you.
Great. Thank you. Thank you for the opportunity to present some of the research we've been doing at Durham University. So today I want to talk to you about a numerical tool that we've been working on to try and explore uncertainty in mine water schemes at the feasibility stage, when you don't have much information at the start of a project. And let's thank my co-authors on this work, Jorin van Hunen, Alexandra Sweeney, Charlotte Adams, and Momoko Hioki. So first I want to introduce a bigger project I'm part of, and it's called GEMS, and it stands for Geothermal Energy from Mines and Solar Geothermal Heat. And as you can see here on this slide, we have quite a lot of partners that span a wide range of sectors. And really what we're trying to do here is to understand both some of the technical, I would say, aspects of mine water heating, which I'm going to be talking today about, but also looking at some of the business, economic, and anthropologic aspects of this technology, to try and really bring everything together. But as I said, today I'm going to talk about specifically the numerical tool that we've been working on, and we've called it GEMS Toolbox. And it kind of has three core axes to it. And the first is that we want a code that runs fast so that we can run it multiple times to give us kind of a probabilistic exploration of the risk profile. So we have a lot of uncertainty, and we want to look at quite a few scenarios to explore that uncertainty, see what the output is, and be able to translate this into kind of project risk. We want to maximize the use of available data. So at the start of a project, you usually don't have much data on the subsurface. You might have a bit of historical data, a few borehole logs. And in the UK, we're quite fortunate that we have a lot of mine plans from the mines, as we've seen today already. And these kind of, even though they are not always accurate, they do provide us a very good idea of where this kind of anthropogenic, high permeability roadways are in the subsurface, which are going to have orders of magnitude greater permeability than the surrounding rock. So it's kind of a good starting point as a modeling input, even though you have to acknowledge that there is uncertainties in these plans. And finally, we want to try and obtain outputs from the model that can be used to support further data acquisitions in the early project stage, and also support decision making in the early stages of the project. So I'm now going to introduce how it works in a nutshell. And basically, the first thing we look at is think of the problem from a geometrical point of view. So as I mentioned, we start by digitizing available mine plans to kind of create an approximate map of the high permeability pathways that will connect our injection and our abstraction borehole. And then what we do is we abstract the volume of rocks in between these roadways, around these roadways. And to do this, we've developed what I would call spatial awareness functions, and allow us to weight different analytical solutions in different parts of the system. And then the other elements is that we're basically looking at the whole lifespan of the project rather than short-term behavior. So if you look at the whole lifespan of the project, it's reasonable to assume steady state flow. And then on top of that, you can overlay time-dependent heat transport to evaluate how the temperature is going to change in your system throughout the years of the site's life. We also put quite a lot of time looking at usability. which is quite challenging to do when you're not from a computer science background. But nonetheless, we've developed a workflow that allows the digitization to be done in ArcGIS. And then I've put together a Excel-based input system so that you do not require any coding to be able to build your inputs into the model and run your code or run your sensitivity analysis on it. And this has proved very useful to work with students who do not have the programming background. And finally, the outputs are compatible with ParaView, which is a free open source piece of software that you can use to make 3D rendering of your data set, so you can see the mine in 3D and the change in temperature over time. So now I'm just going to show you an example of one run here. Durham University. This is a theoretical example, so please do not go around shouting that Durham University is actually going to do a mine water scheme or is undertaking one. This is purely for the purpose of this conference. I wanted to kind of anchor it a bit more on a practical case. And what I've done is I've taken the energy demand from one college's hall of residence, around 1,000 rooms, and took the yearly demand and divided this over the year. And that gives us a flow rate of around 6.5 liters per second to provide around 200 kilowatts of heat to the user. And that's around 1.7 gigawatt hours per year. So it's quite a small system as far as mine water geothermal goes. And this is what the model output looks like in ParaView. So we have a shallow hot seam around 60 meters below the surface, and it's at 11 degrees. You can see in, I don't know if I can, pointers, laser pointer, yeah. The dashed red line here indicates that there is, according to the mine plans at least, there is no connection either side of this red line in the mine workings. Then beneath that, you have the busty seam at around 140 meters below the surface, and that is around 13.5 degrees. You have a shaft connecting the two, and you have hypothetical boreholes here, abstracting from the deeper seam, removing around 5 degrees worth of heat from the water and re-injecting the cooler water at 8.5 degrees into the shallow seam. And what you do is you create a circulation pattern between the two boreholes, and that goes down the shaft and then towards the abstraction point. And you can see that we can combine areas that have been either longwall mined or potentially pillar robbed, where we can estimate that there might be some level of collapse and that the porous medium would be more appropriate. And in other places, we can also couple that to gallery that are open and that can allow free-flowing water. And you can see that the water, the colder water, seeping out and warming up as it travels through the mine before making its way to the abstraction point. One thing you probably took from the previous slide is that the model is quite dense, and therefore one of our students, Momoko Hioki, has been starting to look at simplifying these dense patches of galleries into coarser systems. So she did her thesis on 1 by 1 kilometer with a 50 by 50 set of galleries, and wanted to understand whether it was possible to find an equivalent flow rate that would give you the same outflow temperature with a much coarser system. The reason why she wanted to do this was that because if you have a 10 by 10 grid, you can run the code in less than a second, in a fraction of a second. If you have a 50 by 50, you're looking at 7 seconds. So this could lead to significant speed up times and allow us to model much greater extent of mine plans, essentially. And what she found was that she was able to get a very good match on the outflow temperature. So she compared basically almost manually looking for the flow rate that the full model would predict for the same output via trial and error, a bit more advanced than trial and error, but essentially trial and error. So she got this value. And then she developed a set of equations that were supposed to predict that exact same flow rate. And as you can see, she was able to do this quite well with just a few plans. So this means that it looks like we have a way to start thinking about developing surrogate models for certain sections of the mine plans once we've done an initial simulation. So in conclusion, the GEMS toolbox is a new modeling tool for feasibility stage assessment. This we're currently actively working on. The first stage of the surrogate modeling has been successful, and we are looking to implement seasonal storage and the scaling up of probabilistic and statistical assessments as part of the toolbox. Thank you.